Our universe holds secrets far deeper than we can see. We are about to journey through 30 of the most profound mysteries in space, questions that defy our current understanding of reality itself. By the end, you will grasp the true frontiers of cosmic science and the puzzles that define our place in the cosmos. We will confront the invisible grip of dark matter and ask what truly happened before the Big Bang. What single cosmic question keeps you wondering about it all? The first great puzzle on our list is a substance so ghostly it makes up most of the matter in the cosmos, yet we have never seen it. We call this phantom dark matter. We know it is there because of its immense gravitational pull. Entire galaxies spin so fast that they should fly apart, but an invisible force holds them together. This unseen scaffold dictates the motion of stars and bends the very fabric of space itself. Without its gravitational glue, our universe would look completely different. So what could it possibly be made of? Scientists have proposed exotic particles that barely interact with normal matter. One leading candidate is the WIMP, a weakly interacting massive particle that could be streaming through you right now without a trace. Another is the Action, an ultra-lightweight particle born from theoretical physics. To find them, researchers have built incredibly sensitive detectors deep underground, shielded from cosmic rays in places like an old gold mine in South Dakota. These labs wait in profound silence, hoping to catch the faintest whisper of a dark matter particle colliding with an atom. After decades of searching, the substance comprising roughly 27% of the universe remains a ghost in the cosmic machine. If dark matter is the universe's hidden anchor, then dark energy is its mysterious engine, relentlessly pushing the cosmos apart. This force is even more baffling than its dark counterpart, making up a staggering 68% of everything in existence. Its story began with a startling discovery in the late 1990s. Astronomers were observing distant stellar explosions, known as Type 1, a supernova, to measure how fast the universe was expanding. They expected to find the expansion was slowing down, pulled back by the collective gravity of all matter. Instead, they saw the opposite. The most far-flung supernova were dimmer than they should have been, meaning they were farther away than anyone predicted. The universe was not just expanding, it was accelerating. Something was overpowering gravity itself. That something is dark energy. Think of it as a kind of anti-gravity, a repulsive force woven into the empty vacuum of space. While dark matter pulls galaxies together with its immense gravity, dark energy is doing the exact opposite, tearing the cosmic fabric on the largest scales. Every cubic centimeter of what we call empty space contains this latent energy, and as the universe expands, more space is created, which in turn creates more dark energy. This leads to a runaway effect, a self-perpetuating cycle of acceleration. The ultimate fate of the cosmos may be a cold, lonely one, with galaxies being pushed so far apart that the sky beyond our own local group will one day be utterly black and empty. What could possibly be causing this? The leading idea points to a concept from Einstein's own equations, a cosmological constant representing the energy of empty space. Yet when physicists calculate how strong this vacuum energy should be, their theoretical answer is wrong by a factor of 1 followed by 120 zeros. It is the most embarrassing discrepancy in all of physics. Is dark energy a constant force, or is it something that changes over time, an exotic field we have yet to name? The answer will determine the destiny of everything. This silence is the greatest mystery of all. We live in a cosmos filled with hundreds of billions of galaxies, each one home to trillions of planets. With numbers so vast, the universe should be teeming with life, a vibrant interstellar community. Yet when we listen, we hear nothing but an eerie cosmic quiet. This contradiction is the heart of the Fermi paradox, a puzzle that asks a simple, haunting question. Where is everybody? Decades ago, physicist Enrico Fermi famously captured this idea over a casual lunch, pointing out that any civilization with modest technology and enough time should have filled the galaxy. So why do we see no signs of them, no grand engineering projects, no stray communications, no visitors? To frame this question, astronomer Frank Drake created an equation, a way to estimate the number of active, communicative civilizations in our Milky Way. The Drake equation multiplies factors like the rate of star formation, the fraction of stars with planets, the number of habitable worlds per system, and the probability of life arising, evolving intelligence, and developing detectable technology. Plug in the numbers optimistically, and you might get thousands of advanced societies. Yet our most powerful radio telescopes, listening for decades in programs like SETI, the search for extraterrestrial intelligence, have detected no artificial signal, no cosmic hello. This profound silence forces us to confront a disturbing possibility. Perhaps there is a barrier, a great filter, that prevents life from progressing to the interstellar stage. This filter could be behind us, a rare and miraculous step that we on Earth somehow passed. Maybe the emergence of life itself, or the jump to complex multicellular organisms, is extraordinarily unlikely. If that is the case, we might truly be alone, the only conscious beings in the entire galaxy. The more terrifying alternative is that the great filter lies ahead of us. Perhaps every civilization that reaches our level of technological development inevitably meets its end, destroyed by its own creations, whether through climate catastrophe, nuclear war, or a technology we have not yet even conceived. The empty sky might not be a sign of our solitude, but a grave warning from a universe where intelligence is its own worst enemy. The answer to whether we are alone will define our future, either as cosmic orphans or as survivors who have just passed the universe's most difficult test. The profound silence from the cosmos forces us to look inward to a mystery buried in the very beginning of everything. What happened before the Big Bang? Our current laws of physics simply break down at that moment of infinite density and temperature, a point we call the singularity. Time, as we understand it, may have begun there, making the question of a before almost meaningless. It is like asking what is north of the North Pole, yet our minds rebel against the idea of a definitive start from absolute nothingness. So, physicists speculate about what could have preceded our cosmic dawn. One compelling idea is the cyclic universe, a timeless cycle of cosmic death and rebirth. In this model, our universe is just one page in an infinite cosmic book. It begins with a Big Bang, expands for trillions of years until dark energy tears everything apart, and then contracts back into a single point in a big crunch, only to explode outward once more in a new Big Bang. The universe would have no true beginning or end, only an endless, breathing rhythm of creation and destruction. Another radical proposal is the multiverse. Our Big Bang may not have been a unique event, but merely one bubble inflating in a vast, eternal cosmic foam. In this endless landscape, new universes are constantly bubbling into existence, each with its own unique laws of physics. Our universe, with its perfect conditions for life, would be just one fortunate island in an infinite archipelago of realities. Then there is the most mind-bending possibility of all, that the universe spontaneously emerged from a frothing quantum foam, a seething sea of potential where particles and energy flicker in and out of existence. In this view, the universe truly did come from nothing, a random fluctuation in the fabric of reality that, against all odds, stabilized and inflated into the cosmos we know. We are left to wonder if our entire existence is the result of a single, unimaginably lucky quantum event. The fate of our universe hinges on a single, invisible force, the same dark energy that drives its accelerating expansion. This mysterious pressure will ultimately decide whether the cosmos ends in fire, ice, or a violent tear. The first of these classical scenarios is the Big Crunch, a dramatic reversal of creation. In this fiery end, the expansion of the universe would eventually slow, halt, and then reverse. Galaxies would begin rushing back toward each other, pulled by gravity's unrelenting grasp. Space itself would contract and the temperature would soar. All matter and energy would be compressed back into an ultra-hot, ultra-dense state, a singularity mirroring the Big Bang itself. It is a cosmic cycle of death and rebirth. The second possibility is the Big Freeze, also known as the heat death. This is the most widely accepted forecast based on our current observations. Here, dark energy continues its work, pushing galaxies apart at an ever-increasing rate. Star formation will eventually cease as all the raw gas and dust is used up. Existing stars will burn out one by one, plunging the universe into darkness. Black holes will slowly evaporate over unimaginable eons, and space will become a vast, cold, and nearly empty void. The temperature will approach absolute zero, and all activity will grind to a permanent halt. It is a quiet, cold, and lonely end. The third and most violent option is the Big Rip. In this scenario, dark energy is not just constant, but it actually grows stronger over time. If its repulsive force becomes dominant over even the smallest scales, it would not just push galaxies apart, it would tear everything apart. First, galaxy clusters would be shredded. Then, individual galaxies would be pulled asunder. As the force intensifies, it would rip stars from their solar systems and planets from their stars. In the final moments, it would overcome the forces holding atoms together, shredding every molecule, every atom, and even the very fabric of space-time itself. The entire universe would be dissolved into a mist of fundamental particles, unable to ever interact again. So which path is our universe on? The answer lies in precisely measuring the expansion rate and the strength of dark energy. Astronomers are engaged in a massive effort to chart the cosmos in unprecedented detail, using telescopes to map the distances to millions of galaxies and to study the cosmic microwave background, the faint afterglow of the Big Bang. They are searching for the slightest clue that will tell us if dark energy is constant, weakening, or strengthening. The destiny of every star, every planet, and every atom depends on the outcome of this cosmic investigation. Beyond the ultimate fate of the cosmos lies a place where fate itself has no meaning. A black hole is a region of space where gravity is so intense that nothing, not even light, can escape its grasp. We can understand the physics right up to its edge, the event horizon. This is not a physical surface but a point of no return, a one-way street into oblivion. Once an object crosses this boundary, it is lost to our universe forever. But what happens after that crossing is the greatest enigma in physics. According to Einstein's theory of general relativity, anything that falls into a black hole is irresistibly pulled toward the center, crushed into an infinitely dense point called a singularity. Here, our current laws of physics cease to function. The concepts of space and time break down completely. This idea of a singularity is so problematic that it is essentially physics saying, we do not know what happens here. The conflict deepens with the information paradox. Quantum mechanics, the rules governing the subatomic world, states that information about an object can never be truly destroyed. But if an object falls into a black hole and is lost forever at the singularity, then all information about it is erased from reality. This creates a fundamental contradiction between our two most successful theories of physics. To resolve this, some physicists have proposed a terrifying solution, the firewall hypothesis. This suggests that the event horizon is not a smooth gateway but a blazing wall of high-energy particles that would instantly incinerate anything attempting to cross. While this would preserve information, it violates the principle of equivalence from general relativity, which states that falling through the event horizon should be an uneventful process. So is the event horizon a quiet threshold or a wall of fire? We simply do not know. these bizarre possibilities lead to an even more speculative idea that black holes are not endpoints but gateways. The singularity might not be a dead end but a tunnel, a wormhole connecting to another universe or a different region of our own. In this view, falling into a black hole could be a one-way trip to an entirely new reality, a cosmic rebirth on the other side of space-time. For now, black holes remain the ultimate cosmic vaults, guarding their secrets behind an impenetrable curtain of gravity. The secrets of black holes lead us to a puzzle much closer to home, the origin of life itself. How did inanimate matter first awaken into a living, breathing world? This question echoes far beyond our planet, connecting our existence to the wider cosmos. One of the most compelling theories is panspermia, the idea that life's raw ingredients or even the first simple organisms hitched a ride to Earth from space. Imagine a comet, a frozen relic from the solar system's birth, carrying within its icy heart complex organic molecules. When such a comet slammed into our young planet, it could have delivered a starter kit for life directly to our oceans. We have already found evidence for this. Certain meteorites recovered from places like Antarctica contain amino acids, the fundamental building blocks of proteins. These are not life itself, but they are the very letters needed to write its first sentence. The early Earth was a chaotic and violent place, bombarded by asteroids and comets for hundreds of millions of years. Its surface was a molten hellscape, cooling slowly to form a thin crust over a global ocean. The atmosphere was a toxic mix of methane, ammonia, and carbon dioxide with no breathable oxygen. In this seemingly inhospitable environment, something miraculous happened. Energy from lightning strikes, volcanic vents, or ultraviolet radiation could have provided the spark that transformed those delivered chemical ingredients into the first self-replicating molecule, a primitive ancestor of DNA. This cosmic perspective transforms our search for life elsewhere. We now look at the red dust of Mars with new eyes. The Martian surface, once warm and wet, may have nurtured its own simple life billions of years ago. If so, impacts could have blasted Martian rocks containing microbes into space, where they drifted for eons before falling to Earth. In this incredible scenario, we might all be descendants of Martians. Our robotic rovers are now actively drilling into Martian rock, searching for the fossilized remains or chemical signatures of such ancient life. Every new discovery of organic material on an asteroid or a moon like Enceladus strengthens the possibility that the universe is preloaded with the chemistry of life. The question is no longer just how life began on Earth, but whether it is a local miracle or a cosmic imperative, scattered like seeds across the galaxy by the silent, wandering comets. The idea that our universe is not unique is one of the most staggering in all of science. What if the Big Bang was not a singular creation event, but merely one bubble inflating in an infinite, bubbling cosmic foam? This is the theory of the multiverse. It arises naturally from our best models of the cosmos's earliest moments, a period known as cosmic inflation. This theory posits that right after the Big Bang, space itself expanded at an unimaginable speed, stretching a subatomic speck into a vast cosmos in a fraction of a second. But if this inflationary field exists, quantum physics suggests it might never truly turn off. Instead, it could keep bubbling forever, with each new bubble inflating into its own separate universe, complete with its own Big Bang. Our entire observable cosmos, with its hundreds of billions of galaxies, would be just a single bubble in this endless, frothing sea. String theory, a candidate for a theory of everything, adds another layer to this. It suggests the fundamental properties of our universe, like the strength of gravity or the mass of an electron, are determined by how tiny, vibrating strings of energy are folded into extra, hidden dimensions of space. The mathematics of string theory does not point to one single configuration, but to an astronomical number of possibilities, perhaps 10 to the 500 different ways. Each of these potential configurations could represent a different universe with entirely different laws of physics. In most of these universes, the constants would be wrong for life. Atoms might not hold together, or stars might never form. We exist in this particular universe not because it is special, but because it is one of the rare bubbles where the numbers accidentally allow for galaxies, planets, and conscious beings to arise. This is the anthropic principle in its most dramatic form. The philosophical implications are profound. It suggests that every possible reality exists somewhere. There could be a universe where you made a different choice this morning, or one where dinosaurs never went extinct, or one where gravity is repulsive. The multiverse transforms the question of why our universe is so finely tuned for life from a profound mystery into a simple statistical inevitability. If there are infinite universes, then every possible arrangement of matter and energy must occur somewhere. But can we ever prove it? The greatest challenge is that these other universes are, by definition, beyond our cosmic horizon, separated from us by an uncrossable gulf of inflating space. We cannot see them directly. However, some scientists speculate that if our bubble universe collided with another in the distant past, it might have left a faint imprint on the cosmic microwave background, a bruise on the oldest light in the sky. We are searching for that scar, a pattern in the primordial radiation that defies any other explanation. Finding it would be the ultimate discovery, revealing that we are part of a reality so vast it makes our own universe seem like a single grain of sand on an endless beach. Our understanding of black holes and the multiverse rests on a concept so familiar it feels absolute, yet it is anything but. Time itself is our next great cosmic riddle. We feel its flow as an undeniable current carrying us from a fixed past into an uncertain future. But why does time have a direction at all? The answer appears to lie in a concept known as entropy, which is a measure of disorder in the universe. Think of a hot cup of coffee left on a table. It will always cool down to room temperature, its heat dispersing into the air. You will never see the surrounding air spontaneously give up its energy to reheat the coffee. This is the arrow of time in action, dictated by the second law of thermodynamics, which states that the total entropy of an isolated system always increases over time. The universe as a whole is moving from a state of lower entropy, like the concentrated energy of the Big Bang, toward a state of maximum disorder, the eventual heat death we discussed. Our memories, our sense of cause and effect, are all tied to this irreversible slide into cosmic chaos. But this creates a profound conflict with our most fundamental laws of physics. The equations governing gravity, electromagnetism, and quantum mechanics work perfectly well if time runs backward. They are time-symmetric. At the most basic level of reality, there is no inherent reason for time to flow forward. So why do we experience it so rigidly? Albert Einstein's theory of relativity only deepens the mystery. He showed that time is not a universal constant ticking away the same for everyone. Instead, it is a flexible dimension woven together with space into a single fabric called spacetime. Time slows down the faster you move and even slows near a massive object like a planet. For an astronaut orbiting the Earth, time actually passes slightly slower than it does for us on the surface. This has been proven with incredibly precise atomic clocks. This relativity of time shatters the idea of a single, universal present. Your now and my now are not necessarily the same if we are moving relative to each other. This leads to one of the most mind-bending ideas in all of physics, the block universe theory. In this view, the entire cosmos is a static, four-dimensional block of spacetime. The past, present, and future all exist simultaneously, laid out like frames in a film. Our conscious experience of moving through time is just an illusion, a mental trick as we traverse this frozen landscape. We feel we are moving from one frame to the next, but in reality, every moment from the birth of the universe to its very end is already fixed and real. This means your first birthday and your last are both out there, permanent parts of the cosmic structure. Is the flow of time a fundamental property of the cosmos, or is it merely a side effect of our limited thermodynamic perspective? The answer will forever change how we see our own lives trapped in this fleeting, one-way journey we call the present. The universe should not exist. This is not a philosophical statement, but a conclusion from pure physics. In the first moments of the Big Bang, energy should have condensed into equal amounts of matter and antimatter. For every proton created, an antiproton should have appeared. For every electron, a positron. These pairs are perfect mirror images, destined to annihilate each other upon contact in a flash of pure energy. If the cosmos had followed this perfect, symmetrical script, every particle of matter would have met its antimatter twin, and the entire universe would have dissolved back into a featureless sea of radiation. There would be no stars, no planets, and no one to wonder why. Yet here we are, a universe made of stuff of matter. The very fact that you exist is proof that this perfect balance was broken. Somewhere in that first fleeting second, a fundamental rule was bent. For every billion pairs of matter and antimatter that annihilated, a single particle of matter was left behind. That 1 in a billion survivor is the source of every atom in your body, every star in the sky, and every galaxy stretching out into the darkness. This tiny, monumental asymmetry is known as baryogenesis, the creation of an imbalance where none should be. The hunt for the mechanism behind this cosmic preference for matter has led physicists to a subtle crack in the laws of nature called CP violation. CP stands for charge and parity. It is the idea that if you swap a particle with its antiparticle, which reverses its charge, and then view the interaction in a mirror, which reverses its parity, the physics should look exactly the same. It should be perfectly symmetrical, but in certain exotic particles it is not. Experiments have shown that some particles and their antiparticles decay at slightly different rates. This is the crack we have found, a tiny preference for matter over antimatter in the behavior of specific subatomic particles. The problem is, the amount of CP violation we have observed so far is far too small to account for the overwhelming dominance of matter in our universe. It is like finding a single dropped coin when we need to explain a mountain of treasure. The search is on for new, stronger sources of this symmetry breaking. This is where the world's largest machine comes in. Deep beneath the border of France and Switzerland, the Large Hadron Collider smashes protons together at nearly the speed of light. In the fiery aftermath of these collisions, for a fleeting instant, conditions similar to the early universe are recreated. Detectors the size of cathedrals with names like LHCb and Alice sift through the debris, looking for the telltale signs of exotic particles that might decay in a slightly lopsided way, favoring matter just enough to solve the puzzle. They are searching for a ghost in the machine of creation, a fundamental force or particle that tipped the scales in our favor. The answer is more than a scientific curiosity. It is the reason anything exists at all. Without that 1 in a billion exception, the cosmos would be a silent, empty void. We are the evidence of a broken symmetry, the legacy of a cosmic imperfection that made everything possible. The very existence of matter is a testament to a broken cosmic rule, but that matter did not simply linger. It had to assemble itself into the complex structures we see today. We have a broad story for how stars and planets are born, but the details are riddled with gaps that challenge our understanding. It begins in vast, cold clouds of gas and dust, nurseries where gravity slowly pulls material together. As a dense knot collapses, it spins faster, flattening into a swirling disk of material around a newborn protostar. Within this disk, microscopic dust grains of silicon and carbon begin to stick together, building up like snowflakes in a blizzard. They grow from specks to pebbles and from pebbles to boulders. This is where we hit our first major roadblock, a puzzle known as the meter-size barrier. When these boulders reach about a meter in diameter, the physics of the protoplanetary disk turns against them. Gas swirling around the young star creates a powerful headwind, and these meter-sized rocks are caught in a drag so severe that they are pulled inward, spiraling rapidly toward their fiery doom in the star. They have just decades to overcome this before being destroyed, not nearly enough time to gently bump into each other and grow. It is like trying to build a snowman in a hurricane. How do they cross this barrier to form the building blocks of planets, the mountain-sized planetesimals? We are not sure. Perhaps instabilities in the disk cause pebbles to cluster together in dense clumps, their collective gravity suddenly pulling them into a larger body all at once. Or maybe temporary, low-pressure regions in the gas act as traps, gathering boulders like leaves in a puddle. This initial step from dust to a stable worldlet remains one of the great unsolved problems in planetary science. But an even more pressing mystery involves the giants. How does a gas giant like Jupiter form so incredibly fast? Our leading model, core accretion, suggests a planetary core of rock and ice must first form, growing to about 10 times the mass of Earth. Only then is its gravity strong enough to rapidly pull in the vast envelope of hydrogen and helium gas from the disk. The problem is time. Observations show that the gas-rich protoplanetary disks around young stars only last for a few million years before dissipating. Building a core large enough through the slow process of collisions seems to take longer than the gas disk exists. It is a cosmic race against time, and our models keep finishing late. This has led to an alternative, more dramatic theory, disk instability, where a massive disk could cool and collapse under its own gravity in a mere few thousand years, fragmenting directly into a giant planet without the need for a large core first. Yet, we do not know if this is how our own solar system worked. The Juno spacecraft orbiting Jupiter is right now measuring the planet's gravitational field, searching for clues about whether it possesses a large, compact core, which would support core accretion, or a more diffuse one, hinting at a rapid collapse. The answer will rewrite the story of our own cosmic neighborhood and define how we interpret the thousands of exotic planetary systems we are discovering around other stars. The birth of worlds is a process we are only beginning to decipher, a delicate dance between chaos and gravity that we have yet to fully witness. The delicate dance of planet formation unfolds within a universe whose own fundamental shape remains a profound mystery. We have mapped the local cosmic neighborhood, but the grand architecture of reality itself is our next frontier. What is the true size and shape of the universe? To grasp this, we must first understand that we are not talking about its contents, the galaxies and voids, but the very fabric of space-time upon which everything is painted. General relativity tells us that mass and energy can curve this fabric, and on the grandest scale, the total amount of everything determines the universe's geometry. There are three primary possibilities. The cosmos could be flat, like an endless sheet of paper. It could be closed, like the surface of a sphere, finite but without an edge. Or it could be open, curving outward in a saddle-like shape, extending to infinity. The answer is written in the oldest light we can see, the cosmic microwave background. This is the faint, cold afterglow of the Big Bang, a snapshot of the universe when it was just 380,000 years old, a toddler in cosmic terms. This radiation fills all of space, and by studying its minute temperature variations, its tiny hot and cold spots, we can take the universe's measure. Think of these fluctuations as a cosmic ruler. If the universe is positively curved and closed, the ruler would appear bent, and the patterns in the background radiation would look larger than they truly are. If it is negatively curved and open, the ruler would be shrunken, making the pattern seem smaller. After decades of meticulous observation, from satellites like Planck to ground-based telescopes, the results are in. The data points overwhelmingly to a flat universe. The cosmic ruler shows no distortion. This seems to answer the question, but it only deepens the mystery. A flat universe, according to the rules of general relativity, requires a very specific critical density of matter and energy. The measurements show we have just that, a near-perfect balance. This is astonishingly fine-tuned. If there were slightly more matter, the universe would have collapsed back on itself long ago. Slightly less, and it would have flown apart so rapidly that galaxies never could have formed. This precise flatness hints at something else, a dramatic period of inflation that stretched the infant cosmos to such an immense scale that any initial curvature was smoothed away, like flattening a crinkled sheet by pulling its edges with incredible force. But if the universe is flat, does that mean it is infinite? We do not know. A flat geometry is consistent with an infinite universe, one that simply goes on forever in all directions. This is a staggering concept to grasp. Beyond our observable horizon, beyond the 93 billion light-year sphere of galaxies we can see, more space and more galaxies would continue without end. Every possible configuration of matter would repeat, leading to the mind-bending possibility of infinite copies of Earth and of you. Alternatively, the universe could be finite but trick us with its topology. A flat tabletop can be rolled into a cylinder, having a finite area but no edge. Our universe could be wrapped in a similar, complex shape. If it were small enough, a powerful telescope might theoretically see the back of our own heads, the light from our galaxy having traveled all the way around the cosmos. So far, we have seen no such repetition. The silence suggests that if the universe is finite, it is likely far larger than the patch we can observe. We are left peering into the darkness, wondering if we are a solitary island in a finite sea, or just one tiny speck on the shore of an infinite and endless cosmic ocean. The universe's perfect flatness is a clue to its own violent birth. To explain this fine-tuning, we must rewind the cosmic clock to a moment almost beyond comprehension. What could possibly power the Big Bang itself, transforming a microscopic speck into a macroscopic cosmos in less than a billionth of a billionth of a billionth of a second? The leading answer is cosmic inflation, a theory proposing a burst of hyper-expansion that set the stage for everything to come. This was not an explosion of matter into space, but a runaway stretching of space itself. Imagine a tiny patch of the early universe, smaller than a single proton. Suddenly, a repulsive force of unimaginable strength took hold, doubling the size of that patch again and again, faster than the speed of light. In a span of time so brief it makes a blink seem eternal, that subatomic dot was inflated to a size larger than our entire observable universe. This explains why the cosmos appears so uniform and so flat, just as blowing up a balloon smooths out its wrinkles. But what was the engine for this incredible transformation? Physicists propose the existence of an unknown field, a kind of cosmic fuel that permeated all of space. They call it the inflatoned field. Think of it as a kind of energy credit, a reservoir of potential that the young universe could draw upon. As this field decayed from a high-energy state to a lower one, it released its stored energy, dumping it into the fabric of spacetime and triggering the intense expansion we call inflation. The leftover energy from this decay is what filled the universe with the hot soup of particles that would later become stars and galaxies. The inflatoned field itself then faded away, leaving behind the more familiar forces and particles we know today. But how can we possibly test a theory about an event that happened almost 14 billion years ago? The key lies in the oldest light in the universe, the cosmic microwave background. This faint glow is not just a map of temperature, it also carries a record of ancient vibrations in the form of polarization. The violent expansion of inflation would have sent powerful ripples through spacetime itself, gravitational waves that compressed and stretched the primordial universe. These ripples would have left a distinct swirling pattern, a curl, in the polarization of the cosmic microwave background. Finding this specific fingerprint would be the smoking gun for inflation. It would confirm that the universe really did undergo this fantastically rapid growth spurt and reveal the energy scale at which it happened. Telescopes at the South Pole and in the high Chilean desert are now scanning the sky with incredible precision, searching for this faint, swirling signature imprinted on the cosmic background. Detecting it would be like finding the fossilized heartbeat of the cosmos, a direct echo from the very first moment of creation. Einstein's equations hold a secret doorway hidden within the math. A wormhole is a theoretical tunnel, a shortcut connecting two distant points in spacetime. Picture the universe not as a flat sheet, but as a folded piece of paper. A wormhole would be a pencil hole punched through the fold, creating a bridge that bypasses the long journey across the surface. These cosmic passageways, also known as Einstein-Rosen bridges, are valid solutions to the equations of general relativity. They are not magic, but a potential feature of a universe where space and time are malleable. The problem is not their existence in theory, but their stability in reality. A naturally forming wormhole would be incredibly unstable. The moment it opens, the immense gravitational forces would snap it shut, crushing anything inside into a singularity faster than the speed of light. It would be a tunnel with both entrances slamming shut the instant you try to step through. To hold this doorway open, to prop it against the weight of its own gravity, would require something truly bizarre, exotic matter. This is not just strange or unknown material. Exotic matter is a hypothetical substance that possesses a negative energy density. It would have the property of repelling gravity itself, acting as a kind of cosmic support beam to keep the wormhole's throat from collapsing. While we have glimpsed faint analogues of this negative energy in certain quantum experiments, like the Casimir effect, we have nowhere near the amount needed to stabilize a traversable wormhole. The energy requirements are astronomical, far beyond anything our civilization could ever hope to produce. Even if we could somehow acquire or create this exotic matter, the challenges are staggering. The radiation and tidal forces near the entrance would likely tear any object apart atom by atom. And then there is the ultimate question: could a wormhole be used for time travel? According to some theories, if one end of the wormhole was moved at a significant fraction of the speed of light or placed near an intense gravitational field, time would pass more slowly for that end relative to the other. This would create a time difference between the two mouths. Walking through in one direction might take you into the future, while walking back could, in theory, return you to a point in your own past. This immediately raises the specter of paradoxes, like the famous grandfather paradox where you could prevent your own birth. The laws of physics seem to abhor such loops, and many physicists believe a mechanism, perhaps yet unknown, would always prevent them from forming. For now, wormholes remain one of the most alluring ideas in theoretical physics, a ghost in the equations that teases us with the possibility of unlocking the universe. They are a testament to the power of human imagination, allowing us to explore the deepest implications of our best theories, even if the reality remains forever out of reach. Flying toward our planet right now are atomic fragments carrying more energy than a major league fastball, all compressed into a single, minuscule particle. These are ultra-high energy cosmic rays, the most powerful subatomic bullets in the universe. They strike Earth's atmosphere with a force millions of times greater than anything our most advanced particle accelerators can produce. Each one is a ghost from a cosmic catastrophe, a messenger from the most violent events in existence. The challenge is that these particles are not protons or electrons, but bare atomic nuclei, stripped of their electrons and hurled across the cosmos. Because they are electrically charged, their paths are bent and twisted by the magnetic fields that perm the space between galaxies. By the time one finally reaches Earth, its trajectory is a tangled, useless clue. It is like trying to find the source of a single, specific leaf blown into your yard after a continent-spanning hurricane. We cannot simply point a telescope in the direction it came from. So how do we hunt these phantoms? Scientists have built enormous observatories that do not look up at the sky, but down at the ground. Facilities like the Pierre Auger Observatory in Argentina cover 3,000 square kilometers, an area larger than some small countries. Instead of detecting the cosmic rays directly, which is impossible, they watch for the aftermath. When one of these ultra-high energy particles slams into the atmosphere, it creates a massive shower of secondary particles, a sprawling avalanche of energy that cascades toward the ground. Thousands of water-filled tanks detect the faint glow of this shower as it passes, while specialized telescopes record the fluorescence it creates in the air, a fleeting ghost of ultraviolet light. By piecing together the details of this atmospheric explosion, we can work backward to estimate the original particle's energy and its rough incoming direction. The suspects for these incredible accelerators are the usual cosmic tyrants: an active galactic nucleus, a supermassive black hole at the heart of a distant galaxy, devouring matter and blasting out jets of plasma that could easily propel particles to such phenomenal energies. Or a gamma-ray burst, the death cry of a massive star collapsing into a black hole, focusing its energy into a beam of unimaginable power. Some of the very highest energy events, however, seem to come from empty space, from voids between galaxies where no known engine exists. This hints at something even more exotic, perhaps the decay of super-heavy relic particles left over from the Big Bang, or defects in the very fabric of spacetime itself. Each ultra-high energy cosmic ray that splashes against our sky is a calling card from a universe of extreme violence, and we are only just beginning to read the message. Our galaxy is not drifting aimlessly through the void. The Milky Way, along with our entire local group of galaxies, is caught in a vast cosmic current, all moving toward a specific, mysterious point in space. This relentless pull is directed at a region we call the Great Attractor, a gravitational anomaly of staggering proportions. It acts like a hidden magnet in the depths of space, drawing thousands of galaxies toward it at a breathtaking speed of over 2 million kilometers per hour. But there is a frustrating problem, a cosmic blind spot that has kept its true nature secret. The Great Attractor lies in the direction of the constellation Centaurus, a region of the sky that is obscured by the thick band of stars, gas, and dust that makes up the disk of our own Milky Way. This is the zone of avoidance where the bustling core and spiral arms of our own galaxy block our view, creating a literal blind spot in our map of the universe. It is like trying to see a distant mountain range through a dense personal fog. For decades, this region was a blank space on our charts, its secrets shielded by our own galactic backyard. To penetrate this veil, astronomers had to turn to telescopes that see in wavelengths of light invisible to our eyes. Infrared observatories like the Spitzer Space Telescope can peer through the obscuring dust, revealing the faint heat signatures of galaxies hidden behind the Milky Way's disk. Even more revealing are X-ray telescopes such as Chandra, which detect the high-energy radiation from superheated gas swirling around immense gravitational structures. What these tools have revealed is not a single monstrous object, but something even more grand. The Great Attractor appears to be the heart of the Laniakea supercluster, a filamentary web of galaxies spanning over 500 million light-years. Our own Milky Way is merely a suburban outpost on the fringe of this immense metropolitan area of the cosmos. The pull we feel is the collective gravity of this entire structure, a concentration of mass so vast it dictates the motion of galaxies for hundreds of millions of light-years around it. But the mystery does not end there. The Great Attractor itself seems to be moving, pulled by something even larger and more distant, a colossal assembly of mass known as the Shapley Attractor. We are caught in a cosmic tug of war between these gravitational giants, a dance on a scale so immense it challenges our very perception of place in the universe. The search continues to map the full extent of this hidden architecture, to understand what truly lies in the direction we are all falling. This uncanny cosmic tailoring brings us to one of the most profound questions of all. Why is the universe so perfectly fine-tuned for life? The fundamental forces and constants that govern reality appear to be exquisitely calibrated, as if set by a master watchmaker. If the force of gravity were even slightly stronger, the universe would have collapsed back on itself in a fiery crunch shortly after the Big Bang. Just a fraction weaker, and matter would never have clumped together to form the first stars and galaxies. The nuclear forces that bind atoms are equally precise. A tiny change in the strength of the strong nuclear force, and protons could not stick together, meaning atomic nuclei would never form. There would be no carbon, no oxygen, and no chemistry at all. The universe would be a boring soup of hydrogen. Even the amount of dark energy is bizarrely perfect. A little more, and the universe would have ripped itself apart before stars could form. A little less, and gravity would have pulled everything back together too soon. It seems every dial on the cosmic control panel is set to an exact value that allows for complexity, planets, and ultimately, us. This staggering coincidence is known as the fine-tuning problem. So how do we explain it? One compelling answer is the anthropic principle. In its simplest form, it states that we observe a universe compatible with our existence because we are here to observe it. In a universe that was not fine-tuned, no one would be around to ask the question. This can feel like a tautology, but it gains power when combined with the multiverse. If an infinite number of universes exist, each with different random constants, then it is no surprise we find ourselves in one of the rare, life-permitting ones. Our universe is not special, it is just lucky. We are the winners of a cosmic lottery. Yet for some, this explanation is unsatisfying. It pushes the fine-tuning one step back, forcing us to ask why a multiverse with such varied laws should exist at all. Are there other, more fundamental physical principles that we have not yet discovered, principles that dictate these specific, life-friendly values? Could our universe be a simulation, its parameters intentionally set by some advanced intelligence? Or is the fine-tuning a genuine mystery, a pointer toward a deeper, unified theory that will one day make these seemingly arbitrary numbers seem inevitable? The search for that theory is the great quest of modern physics. Every time we measure a constant with greater precision or discover a new particle, we are testing the boundaries of this cosmic coincidence, seeking the reason behind a universe that seems, against all odds, made for us. Out of the silent darkness comes a flash brighter than a billion suns. These are fast radio bursts, mysterious cosmic sirens that scream for just a millisecond before vanishing back into the void. Detected as intense spikes of radio waves, these events travel across billions of light years, carrying more energy in their brief flash than our sun will emit in 80 years. The first one was discovered in 2007, buried in archived data from a radio telescope in Australia, and since then hundreds more have been detected. The sheer power is staggering, but the real mystery lies in their origin. How can something release so much energy so quickly and from such incomprehensible distances? Pinpointing the source of these flashes is a monumental challenge. Because they are so brief, traditional telescopes often cannot swing into position fast enough to see the afterglow in other wavelengths of light, like X-rays or visible light. It is like trying to find the location of a camera flash in a pitch-black stadium. The light is gone before you can even turn your head. This has led to a cosmic detective story with a host of compelling suspects. One of the most promising culprits is the magnetar, a type of neutron star with a magnetic field so powerful it could erase a credit card from half the moon's distance away. These cosmic magnets are known to have starquakes and colossal magnetic eruptions, events violent enough to potentially generate such a brilliant, fleeting burst of radio waves. In a thrilling development in 2020, astronomers linked a fast radio burst to a known magnetar within our own galaxy. providing the first direct evidence that at least some of these events come from these magnetic monsters. But magnetars might not be the only source. Another possibility involves the cataclysmic merger of two neutron stars, a collision that ripples space-time with gravitational waves and could, in its final, violent moments, unleash a fast radio burst. This would typically be a one-time event, the final death cry of a system. Yet the plot thickens with the discovery of repeating fast radio bursts. Some sources from the depths of intergalactic space flash again and again, sometimes in a predictable pattern, sometimes at random. This repetition rules out a one-time cataclysm like a merger. What natural engine can power these repeated cosmic hiccups? Could it be a neutron star orbiting a black hole, with material being torn from the star periodically? Or perhaps a highly magnetized neutron star processing like a wobbly top, its beam of radiation sweeping past Earth at regular intervals. The sheer strangeness of these repeating signals has inevitably sparked more speculative ideas. Could they be the result of alien technology? Perhaps they are power beams for interstellar light sails, or simply the leakage from a truly colossal, galactic-scale communication system. While this is the least likely explanation, it highlights just how perplexing these signals are. Each new detection adds a piece to the puzzle, but we are still far from a complete picture. These millisecond messages are cosmic telegrams from the edge of known physics, and we are only just beginning to decode them. The universe runs on forces with wildly different strengths, a disparity so extreme it defies common sense. Gravity, the force that holds galaxies together, is astonishingly feeble compared to the other fundamental forces. The electromagnetic force that binds atoms is a trillion times stronger. This immense gap is known as the hierarchy problem, and it points to a deep crack in our understanding of physics. Why is gravity such a weakling? The answer may lie with a very special particle, the Higgs boson. This particle is responsible for giving all others their mass, acting like a cosmic molasses that slows them down and makes them tangible. Yet the Higgs itself is surprisingly light. According to our best theories, quantum fluctuations should have driven its mass to an unimaginably high scale, to a value quadrillions of times heavier than what we actually observe. It is as if a feather were somehow resisting the crushing weight of an entire ocean. For the Higgs to remain so lightweight, a miraculous and perfect cancellation must occur between these immense quantum effects, a tuning so precise it seems unnatural. Physicists find this level of fine-tuning deeply unsatisfying, believing a more elegant mechanism must be at work. One leading proposal is supersymmetry, a beautiful theory that postulates every known particle has a hidden, super-heavy twin. These superpartners would perfectly cancel out the quantum corrections pushing the Higgs mass upward, solving the hierarchy problem with a single, symmetrical stroke. The only catch is that we have not found any of these superpartners despite extensive searches at the Large Hadron Collider. Their absence suggests that if supersymmetry is real, it must be broken, meaning the superpartners are far heavier than hoped, pushing the problem into new territory. Another radical solution involves the very fabric of space itself. What if gravity only seems weak because it is leaking into extraspatial dimensions, dimensions curled up so tiny we cannot perceive them? In this brain world scenario, our entire universe could be a three-dimensional membrane or brain floating within a higher dimensional space. The strong nuclear and electromagnetic forces are pinned to our brain, but gravity, uniquely, can seep out into the bulk of these extra dimensions. Its strength would be diluted across this vast hidden landscape, explaining why it feels so weak to us confined to the brain. This would mean that on very small scales, gravity could become incredibly strong, a prediction we might one day test in particle colliders. Each of these ideas represents a profound shift in our cosmic perspective, suggesting that the hierarchy problem is not a flaw but a clue, a signpost pointing toward a deeper, more unified reality hidden just beyond our current reach. The weakness of gravity hints at a reality far stranger than it appears. Our daily existence is confined to 3 dimensions of space and 1 of time, a familiar stage of length, width, depth, and duration. Yet, some of our most promising theories of the cosmos insist this is not the whole story. To make the math of the universe work, physicists propose the existence of extra dimensions, hidden realms coiled into a space so tiny we cannot perceive them. Imagine a single strand of hair. From a distance, it looks like a simple one-dimensional line. But if you could shrink down to a microscopic scale, you would see it has a circular thickness, a second dimension curled around its length. Our entire universe might be structured in a similar way. We easily move through the 3 large, expansive dimensions, but at every single point in space, there could be 6 or 7 additional dimensions, curled up into a complex, infinitesimally small shape. This idea is a cornerstone of string theory, which suggests the fundamental constituents of reality are not point-like particles, but vibrating loops of energy or strings. For the mathematics of string theory to be consistent, these strings must vibrate in a universe with 10 or 11 dimensions. The specific way these extra dimensions are folded and curled, a process called compactification, would determine the properties of our reality. The vibrational pattern of a string in this higher dimensional space would manifest as a specific particle with a specific mass and charge. In essence, the electron, the quark, and the photon would all be the same type of string, just vibrating to a different tune in the hidden dimensional symphony. The reason we do not see these dimensions is that they are smaller than an atom, smaller than a proton, perhaps even at the Planck scale, a size so minuscule that it is a billion trillion times smaller than the nucleus of an atom. So how could we ever prove they are real? Scientists at the Large Hadron Collider are attempting to do just that. One tantalizing possibility is that the immense energy of particle collisions could, for a split second, create a particle that is able to move into these extra dimensions. From our 3-dimensional perspective, this particle would simply vanish, carrying its energy away with it. Detectors would see a clear signature of missing energy, an event where the energy before and after a collision does not add up, with nothing to account for the loss. Another, even more dramatic prospect is the creation of microscopic black holes. In a universe with extra dimensions, gravity's apparent weakness could be explained because it is diluted across these hidden realms. At the incredibly small scales probed by the collider, gravity could become unexpectedly strong. If that is true, smashing protons together at near light speed could concentrate enough energy to warp space-time into a tiny, fleeting black hole that would instantly evaporate in a shower of particles. Finding either of these signatures would be a revolution, throwing open a door to a cosmos of unimaginable complexity happening all around us, just beyond the reach of our senses. This fundamental rift in physics leaves a hole in our understanding of reality itself. We have 2 incredibly successful theories that govern the cosmos, yet they are utterly incompatible. On one hand, we have Einstein's general relativity, a masterpiece that describes gravity as the elegant curvature of space-time around planets, stars, and galaxies. It paints a beautiful, continuous picture of the cosmos on its largest scales. On the other hand, we have quantum mechanics, the rulebook for the subatomic world. It describes the other 3 fundamental forces and tells us that the universe is a fuzzy, probabilistic, and discrete place, where particles pop in and out of existence and things like position are never perfectly defined. The problem is stark. General relativity breaks down at the center of a black hole and at the moment of the Big Bang, where densities become infinite. Quantum mechanics, for its part, has no way to include gravity in its description of particle interactions. Unifying these 2 pillars into a single theory of quantum gravity is perhaps the greatest challenge in all of modern physics. One of the most famous contenders is string theory. It proposes that the fundamental building blocks of the universe are not point-like particles, but unimaginably tiny, vibrating loops of energy or strings. Just as a single violin string can vibrate at different frequencies to produce different musical notes, these cosmic strings vibrate in unique ways to create the different particles we observe. An electron is one vibrational pattern, a quark is another, and the photon is yet another. Crucially, one of these vibrational patterns perfectly describes the graviton, the hypothetical particle that would carry the force of gravity. In this framework, gravity is seamlessly woven into the quantum tapestry. The cost, however, is immense. For the math of string theory to work, it requires the universe to have not just 3 dimensions of space, but 10 or even 11. The extra dimensions are theorized to be curled up into shapes so small we could never perceive them. Another major candidate takes a very different approach. Loop quantum gravity does not try to reinvent all of physics. Instead, it focuses solely on quantizing spacetime itself, applying the principles of quantum mechanics directly to the gravitational field. In this view, space is not a smooth, continuous backdrop. It is woven from a fabric of tiny, finite loops, a network of intersecting threads. Picture a very fine, shimmering spiderweb where each connection represents a tiny, indivisible unit of space. This structure prevents the infinities that plague general relativity, meaning there is no such thing as a true singularity. There is a smallest possible volume, a quantum of space. Time, too, would be granular, advancing in these tiny, discrete steps rather than as a continuous flow. While string theory aims to be a theory of everything, loop quantum gravity aims to be a background, independent theory of just gravity, where space and time emerge from the relationships between these loops. The quest to test these ideas is monumental. The energies required to see the granularity of space or the vibrations of strings are far beyond anything our particle colliders can reach. Yet, scientists are searching for indirect clues. They are studying the cosmic microwave background for imprints of the universe's quantum origins, and watching for subtle differences in the behavior of particles over vast distances that might reveal the discrete structure of spacetime. The discovery of quantum gravity would be a revolution, finally revealing the true, unified nature of our reality, from the smallest speck to the grandest cosmic horizon. 4 billion years ago, the inner solar system became a shooting gallery. This era, known as the Late Heavy Bombardment, was a time of unimaginable violence when asteroids rained down upon the young planets, leaving behind the scarred faces we see today on the Moon and Mercury. The evidence is written in the Moon's ancient craters, whose rock samples tell a story of a cataclysm that peaked long after the planets themselves had formed. Why would such a devastating wave of impact suddenly begin, hundreds of millions of years after the solar system's birth? The leading suspect is a cosmic dance of the giant planets, a dramatic rearrangement known as the Nice model. This theory suggests Jupiter, Saturn, Uranus, and Neptune did not form in their current orbits. Instead, they were initially packed much closer together, nestled in a compact configuration beyond the infant rocky worlds. A delicate gravitational balance held them in place until it was disrupted, perhaps by the slow scattering of countless small planetary building blocks left over from the solar system's formation. As these icy planetesimals were gravitationally kicked outward, they pushed back on the giant planets, forcing a migration. Jupiter moved slightly inward while Saturn, Uranus, and Neptune drifted outward. The key moment came when Saturn's orbit reached a precise resonance with Jupiter's, meaning for every 2 orbits Jupiter completed, Saturn would complete one. This created a powerful, rhythmic gravitational pulse that violently shook the entire solar system. The asteroid belt, once a stable reservoir of material, was suddenly stirred into a frenzy, flinging countless rocks inward toward Mars, Earth, Venus, and Mercury. Neptune may have even swapped places with Uranus, hurling a vast cloud of icy comets from the outer reaches into the inner solar system as well. The result was an age of fire, a geological dark age for Earth that may have vaporized its early oceans and repeatedly sterilized its surface, posing a formidable challenge for the emergence of life. Yet the debate is far from settled. What was the precise trigger that set this planetary migration in motion? Was it the gradual dispersal of the planetesimal disk, or could it have been the gravitational influence of a passing star, a stellar sibling from the Sun's birth cluster that has long since drifted away? The timing of the bombardment is crucial, as it coincides with the earliest tentative evidence for life on Earth. Did this cosmic chaos deliver the water and organic compounds that made our world habitable, or did it repeatedly snuff out life's first fragile sparks? The late heavy bombardment stands as a pivotal, violent chapter in our origin story, a period whose cause remains locked in the orbital dynamics of our planetary family. A cosmic web of invisible force stretches between the stars, from the protective bubble surrounding our own Earth to the immense fields threading through entire galaxies. Magnetism is a fundamental yet deeply mysterious feature of the cosmos. We understand part of the story through a process known as the dynamo effect. Picture our planet's molten iron core, a spinning, churning sea of liquid metal. This moving, electrically conductive fluid acts like a colossal electrical generator. As it rotates, it amplifies any existing weak magnetic field, transforming the planet's rotational energy into a powerful planetary magnet. This self-sustaining loop is what creates the protective shield that deflects harmful solar radiation, making our world habitable. The same basic principle applies to stars, including our Sun, where the turbulent motion of plasma generates and twists its magnetic field, leading to sunspots and solar flares. The dynamo is a brilliant explanation for how magnetic fields are maintained and amplified, but it presents a chicken and egg problem. A dynamo cannot start from nothing. It requires a tiny seed magnetic field to amplify. So where did that first, faint magnetic field come from in the early universe? Before the first stars ignited, before the first galaxies formed, what process could have imprinted magnetism onto the primordial cosmos? One possibility involves the universe's violent infancy. In the seething plasma of the Big Bang, tiny differences in pressure and temperature could have created weak electric currents, which in turn generated the universe's first magnetic whispers. Another idea points to the era of first light, when the first stars and galaxies began to form. The shock waves from the first supernova, rippling through the pristine gas of the early cosmos, might have been powerful enough to generate those initial seeds. There is even a more exotic proposal that these fields are a relic from the universe's very first moments, an imprint left over from cosmic inflation stretched to cosmic proportions. Detecting the faint signature of these primordial magnetic fields is an active frontier of astronomy. Scientists search for their subtle influence on the cosmic microwave background, the oldest light in the universe, or for the way they might twist the light from the most distant quasars. Finding this fossil trace would be like discovering the first spark that lit a cosmic fire, the initial push that led to the magnetic tapestry now woven through the void. Far beyond the orbit of Neptune, in the frigid darkness at the edge of our solar system, a ghost is pulling on the strings of reality. The evidence for this phantom world, a hypothetical Planet 9, comes not from a direct sighting, but from the strange, synchronized dance of small, icy bodies in the Kuiper belt. These distant objects, known as trans-Neptunian objects, do not follow random, scattered paths as we would expect. Instead, their orbits are mysteriously clustered, their points of closest approach to the Sun all bunched together and tilted in the same direction, as if an unseen shepherd is herding them. The odds of this alignment happening by pure chance are astronomically small, less than 1 in 10,000. The most elegant explanation is the gravitational hand of a massive, undiscovered planet, a world with perhaps 5 to 10 times the mass of Earth, orbiting the Sun on a long, elliptical path that takes it 20 times farther out than Neptune. This hidden giant would be the true king of the deep solar system, its immense gravity orchestrating the ballet of these smaller worlds from the shadows. Finding it, however, is a monumental task. Its great distance means it reflects almost no sunlight, making it incredibly faint. Its slow, ponderous orbit means it might take 15,000 years or more to complete a single trip around the Sun, so it moves very little in our sky from year to year. Astronomers are scanning the heavens with the world's most powerful telescopes, using complex algorithms to sift through petabytes of data, searching for that one faint dot moving against the backdrop of fixed stars. They are looking for the needle in the ultimate cosmic haystack. The discovery of Planet 9 would be a revolution, rewriting the story of our own cosmic backyard. Its existence would suggest our solar system's formative years were far more dynamic and chaotic than we thought. How did such a large world end up so far away? It may have been flung outward in a gravitational tug-of-war with Jupiter and Saturn during the solar system's violent youth, a cosmic exile banished to the frozen periphery. Its composition and orbit would be a fossilized record of that ancient planetary migration, offering clues about the original cloud of gas and dust that gave birth to our Sun and all its planets. This hidden world is a reminder that our maps of the solar system are still incomplete, that a colossal neighbor could be lurking in the vast, unexplored dark, waiting to be found. The Sun's surface simmers at around 10,000 degrees Fahrenheit, a temperature that feels intuitively right for a ball of seething nuclear fire. Yet, just above this visible layer, in the wispy outer atmosphere called the corona, the heat soars to millions of degrees. It is as if you walked away from a campfire and with each step the air grew hotter instead of colder. This baffling reversal is the coronal heating problem, one of the longest-standing puzzles in solar physics. The corona is the ghostly halo visible during a total solar eclipse, a pearly crown of plasma stretching millions of miles into space. How this ethereal veil becomes so staggeringly hot, while the dense surface below is comparatively cool, defies all basic intuition about heat and energy. The leading suspect is the Sun's own tangled magnetic field. The solar surface is a churning, turbulent place, and this motion constantly twists and stresses the magnetic field lines that arc up into the corona. Think of these field lines as incredibly taut rubber bands. When they are stretched and wound too tightly, they can snap and reconnect in a process known as magnetic reconnection. This sudden reconfiguration releases colossal amounts of energy in tiny, ubiquitous explosions called nanoflares. Each one is minuscule compared to a full-sized solar flare, but they could be happening constantly, millions of them every second, collectively dumping enough heat into the corona to account for its incredible temperature. It would be like heating a room not with a single bonfire, but with trillions of microscopic matches popping off all at once. The other primary theory focuses on waves. The Sun's convective turmoil generates powerful waves that travel upward along the magnetic field lines, much like the vibrations that travel along a plucked guitar string. As these waves, called Alfvén waves, move from the dense surface into the incredibly thin corona, their energy becomes more concentrated. They can break like ocean waves crashing on a shore, dissipating their energy as intense heat directly into the coronal plasma. The true answer might be a combination of both mechanisms, a constant, stormy symphony of magnetic reconnection and wave heating. The immense challenge is that these processes happen on incredibly small scales and at ferocious speeds, making them nearly impossible to resolve with current telescopes. We are trying to pinpoint the exact moment a magnetic field line snaps or a wave breaks in a sea of million-degree plasma from 93 million miles away. Solving this mystery is not just an academic exercise. The corona is the source of the solar wind, a stream of charged particles that influences the entire solar system. Understanding how it is heated is key to predicting the space weather that can disrupt satellites, power grids, and the safety of astronauts. the sun's hidden furnace remains one of its most vital and elusive secrets. Even the most carefully planned missions can whisper a mystery long after they have fallen silent. The Pioneer anomaly began as a faint, persistent signal in the navigational data from the Pioneer 10 and Pioneer 11 spacecraft. As these twin probes journeyed beyond the orbit of Pluto, hurtling into the dark, scientists tracking their trajectories noticed something strange. Both spacecraft were experiencing a tiny, constant, and unexplained deceleration back toward the sun. It was an impossibly subtle pull, weaker than a billionth of the gravity we feel on Earth, but it was there, a phantom tug on humanity's first interstellar messengers. For decades, this minuscule drift defied all conventional explanation. It was too small to be caused by the gravity of known planets or asteroids. It did not match the predicted effects of the solar wind or the drag from interplanetary dust. The anomaly became a source of intense speculation, a hint that our understanding of gravity itself might be incomplete at the outer edges of the solar system. Some theorists proposed new physics, suggesting modifications to Einstein's theory of general relativity or the existence of unseen, diffused dark matter exerting a gravitational pull. The mystery endured because the Pioneer probes were uniquely suited to reveal it. Unlike later spacecraft that used spinning thrusters for stability, the Pioneers were stabilized by spinning themselves, making their trajectory exceptionally clean and easy to model. Every small force acting upon them, from the gentle pressure of sunlight on their antennae to the tiny release of heat from their nuclear power sources, had to be meticulously accounted for. And that is where the answer finally emerged, not from rewriting the laws of physics, but from an exhaustive, years-long forensic investigation. A team of researchers tracked down decades-old engineering documents and telemetry data, even recovering original data from vintage magnetic tapes. They built a complex thermal model of the spacecraft, and they discovered the culprit, heat. The plutonium in the probe's power generators produced a steady stream of warmth, and this heat radiating from the electronics compartments and bouncing off the back of the spacecraft's large dish antenna was providing a tiny, constant push. Just like photons of light, thermal photons carry a minuscule amount of momentum, and when they were emitted preferentially in one direction, they acted as a gentle brake. This thermal recoil force perfectly accounted for the anomalous deceleration. The Pioneer anomaly stands as a powerful lesson in cosmic detective work. It shows how the universe can hide profound questions in the tiniest of details, and how the path to an answer often requires not a revolution, but a return to the fundamentals, a patient and meticulous accounting of every single force, no matter how insignificant it may seem. The universe might be a hologram, a magnificent illusion of depth projected from a flat, two-dimensional surface. This is not science fiction, but a serious proposal known as the holographic principle, and it emerges from the fiery edges of black holes. When an object falls into a black hole, it seems to vanish, taking all information about itself with it. This violates a core rule of quantum mechanics, which states information can never be destroyed. To solve this paradox, physicists discovered that all the information describing the objects that fall in is not lost at the singularity, but is perfectly encoded and preserved on the black hole's event horizon, its one-way boundary. The three-dimensional information of the falling star is painted onto the two-dimensional surface of the horizon, like a fantastically complex and tiny tattoo. The holographic principle boldly suggests this might be true for the entire cosmos. Our seemingly vast three-dimensional universe with its galaxies, planets, and people could be a projection from a distant two-dimensional shell that contains the master code for everything we see and feel. Think of a credit card hologram, a flat sticker that creates a stunning image with apparent depth. Our reality could be a cosmic version of this, a projection from the outer boundary of space itself. If this is true, then space-time is not smooth and continuous as Einstein believed, but is pixelated, composed of tiny, fundamental units of area, a cosmic canvas with a finite resolution. This pixelation would be unimaginably fine at the Planck scale, but its effects might be detectable. Scientists are searching for this graininess in the oldest light in the universe, the cosmic microwave background. They are analyzing the faint patterns in this primordial glow, looking for a specific kind of noise or blur that would be the signature of a pixelated reality, the static of the cosmic projector. If found, it would mean that everything we consider real, from the flight of a bird to the spin of a galaxy, is a holographic expression of information stored on the farthest edge of everything. The moon holds a secret in its silent, gray rocks. Samples brought back by Apollo astronauts contain a startling clue: tiny mineral crystals locked in a specific alignment. This fossilized magnetism proves the moon once possessed a powerful global magnetic field, a protective shield similar to Earth's. This is deeply puzzling. Today, the moon is a largely inert world with a small, cold core that shows no signs of a planetary dynamo. How could this small, cooling body have ever generated such a force, and why did it vanish? The leading theory points to a dramatic, long-vanished power source. In its youth, the moon's interior was still molten from the colossal energy of its formation, the titanic impact that tore it from a proto-Earth. As this lunar magma ocean began to cool and crystallize, dense, radioactive elements like potassium and thorium may have sunk toward the core. This radioactive decay would have provided a potent, long-lasting heat source, churning the moon's liquid iron core. This movement, combined with the moon's faster initial spin, could have powered a dynamo, turning the lunar interior into a giant, spinning magnet. But the moon, being so much smaller than Earth, was destined to cool quickly. Its internal heat engine would have gradually sputtered and died as the radioactive fuel was spent and the core solidified. The magnetic field faded away, leaving the moon exposed to the full fury of the solar wind. Another compelling idea suggests the field was not self-generated but was borrowed. The young moon orbited much closer to a molten, highly magnetic Earth. As it swept through our planet's powerful magnetosphere, the interaction may have induced a temporary magnetic field in the moon's own core, a ghostly echo of Earth's protection that lasted only as long as the two worlds remained in close embrace. The mystery of the moon's magnetic heart is more than a lunar curiosity. It forces us to rethink how small, rocky worlds live and die. If a body as seemingly dead as the moon once had the dynamism for a global shield, then what other quiet worlds in distant solar systems might have hidden histories of their own? The answer is written in the ancient rocks, a testament to a time when the moon was a far more active and vibrant world. The silence was broken for just 72 seconds. In the summer of 1977, a volunteer for the SETI project at Ohio State University's Big Ear radio telescope was reviewing a computer printout when he saw it, a string of letters and numbers so startling he circled it in red pen and wrote a single, exuberant word beside it: "Wow." This was the signal, a burst of intense, narrowband radio waves that seemed to scream artificiality. It came from the direction of the constellation Sagittarius, and it was over 1,000,000 times stronger than the background noise of space. Its frequency was tuned to 1420 MHz, a protected band where natural celestial sources are forbidden to broadcast, a quiet channel reserved for the whisper of hydrogen, the most common element in the universe. It was exactly what scientists had predicted an interstellar message would look like, a clean, powerful beacon cutting through the cosmic static. The signal's intensity rose and fell in a perfect curve over 72 seconds, precisely matching the window of time the Big Ear telescope's fixed dish would have observed a single point in the sky as the Earth rotated. It was a perfect match for a distant, pinpoint source, and then it was gone. Despite decades of follow-up observations with far more sensitive equipment, listening intently to that same patch of sky. The signal never returned. It was a one-time event, a cosmic shout that vanished into an eternal silence. Could it have been a human transmission reflected off a piece of space debris? The frequency was illegal for earthly transmitters, and no known satellite or spacecraft matched the profile. Was it a natural astrophysical event, some previously unknown quirk of a comet or a distant star? No natural phenomenon we have ever discovered can explain its specific, artificial-looking characteristics. The WOW signal remains a perfect, solitary mystery, a ghost in the machine of cosmic search. It is a tantalizing piece of evidence that suggests, just for a moment, we might not have been alone. It is the one signal that fits the profile perfectly, a candidate that has never been dethroned, yet one we can never confirm. It stands as a monument to both the hope and the profound frustration of the search for extraterrestrial intelligence, a single, enigmatic hello that we have spent a lifetime trying and failing to answer. The WOW signal fades into the cosmic background noise, a reminder of the vast distances that separate even potential civilizations. But what if the universe itself offers a loophole, a way to bend the very stage upon which we stand to conquer those impossible gulfs? Our final question dares to dream on a truly cosmic scale. Can we ever achieve warp drive? The idea is not to build a faster ship, but to build a moving piece of spacetime. Imagine a surfer riding a wave. The surfer does not move through the water itself, but is carried forward by the wave's shape. A warp drive would do the same for a spacecraft. It would contract the spacetime in front of it while expanding the spacetime behind it, creating a wave that carries the ship forward while the ship itself sits motionless inside a bubble of flat space. This is not science fiction, but a real solution to Einstein's equations of general relativity proposed by physicist Miguel Alcubierre. The ship would not break the speed of light within its bubble. It would simply let the fabric of the cosmos do the moving, effectively allowing for faster-than-light travel without the paradoxes. The catch, however, is monumental. To create this warp bubble, you would need a form of matter with negative energy density, the same exotic matter required to prop open a wormhole. This is not just rare, it is something we are not sure can exist in the stable, macroscopic quantities required. You would need a ring of this exotic material around your ship, a ring with a mass energy equivalent to perhaps Jupiter, just to create a bubble large enough for a small spacecraft. Then there is the problem of control. How do you start the process, and more terrifyingly, how do you stop? Some calculations suggest that as you decelerate, the particles piling up at the front of your warp bubble would be blue-shifted to impossibly high energies. This would create a blast of Hawking radiation so intense it would vaporize anything at your destination the moment you arrived. You would essentially be firing a cosmic ray gun at your target planet. Furthermore, you would have no way to communicate with the outside universe from inside the bubble, and you could not see where you were going, making navigation a literal shot in the dark. The warp drive represents the ultimate engineering challenge, one that requires us to master the fabric of reality itself. It is a testament to human ingenuity that we can even conceive of such a thing, a machine that rides the wrinkles of spacetime. For now, it remains a beautiful dream, a mathematical ghost in the equations of gravity, reminding us that the universe's greatest secrets might not be in the stars, but in the hidden geometry of the empty space between them. From the phantom tug of dark energy to the silent scream of the WOW signal, we are surrounded by cosmic riddles. These 30 questions are not a list of our ignorance, but a map of the frontier. They represent the very edge of human knowledge, the place where our understanding dissolves into wonder. For every answer we find, the universe seems to present 10 new, more profound mysteries. This is the thrilling, humbling reality of science, a perpetual journey into the unknown. The cosmos does not give up its secrets easily, and the fact that we can even ask these questions is a testament to our own extraordinary capacity for curiosity. So the next time you find yourself under a clear night sky, look up and remember that you are not just looking at points of light. You are gazing at a living, breathing frontier filled with invisible matter, hidden dimensions, and forces we have yet to name. The greatest discoveries are still out there, waiting. The next clue could be found in the data of a new telescope, in the equations of a brilliant mind, or perhaps even in the curious spark of someone just like you, looking up at the stars and daring to ask.